Okay, welcome again. So today let us see different types of load, and because of the load, what are the different type of stresses caused in any machine component. So when we think about the types of load, so the load can be of different types. So look at the presentation. Load is defined as an external force acting upon a machine part. In first two types, the load can be dead or steady load or live or variable load. What is difference between these two? Look at the figure. The construction, the structure which is not going to move in the reference to time is the dead load. So it is permanent load acting on any machine. So foundation of machine is the dead load. Okay. Now what is live or variable load? So in our lathe machine, the headstock, the carriage, which is moving part. So that can be a variable load or live load. If you just observe the figure, you will find that the structure is dead load and people and furniture are the live load in our simple example. Second type of load is suddenly applied load or shock load or impact load. Here, when the load is applied suddenly, then it creates a shock load, or it also called as shock load. In that, the load is applied at a particular moment, at a particular time. Then it is called as a suddenly applied. Now, if the same load is applied with some initial velocity, then it is called as the impact load. So what is difference here? Just if I say the nail is hammered, so generally we have some initial velocity and we are going to hammer that. So it is impact load. Okay. So if I put something suddenly on that machine, then it is suddenly applied load. So that it is the simple classification of types of load. Now these loads causes some resistance inside our machine component. So what is that, what it causes, that we'll see. Now look at the picture. Inside the picture you'll observe that there is one machine component which is subjected to axial load, and because of the axial load there is an elongation of material. Because of that particular force, it causes internal resistance. You can observe that internal resistance by some different color. Here blue color is the original color, but when the force is applied it turns to green. So there is internal resistance observed. So what it called? So let us see in the definition. So internal resistance offered by the body on the various cross section due to some externally applied forces is called as a stress. So whenever any machine component is subjected to force, it causes internal resistance. That internal resistance is called stress. If I say mathematically, the stress is the ratio of force divided by area. Force is generally measured in Newton. Cross-section area is measured in mm square or meter square. So the unit of stress is Newton per mm square or Newton per meter square. Newton per mm square is also called as megapascal. So this is about the stress. Because of the stress, there is elongation. If there is a elongation of the body, then there is one more term which we call as a strain. So how we can define strain? When the load is acting on the body, it undergoes some deformation. That deformation per unit length or per length is called as a simply strain. So whatever deformation is there, that deformation divided by original length is called as a strain. If you just take a mathematically, then mathematically strain is elongation divided by original dimension. So in this particular case, there is elongation in length. So delta L is the elongation divided by original length is L. So delta L change in length is also in same quantity and original length is also in the same unit quantity. So strain is unitless quantity. Okay. So strain is a simply elongation divided by original length. So whenever there is elongation in particular direction, there is a change in the other dimension also. So that's why strain is lateral or longitudinal strain. Okay. Now, whatever type of loading depend upon the direction of loading, we have different kinds of stresses. So if you just look at this particular our presentation, you will find that there are mainly 6 type of stresses that we can observe: tensile stress, compressive stress, shear stress, bending stress, crushing stress. Crushing stress is also called as bearing stress or torsional shear stress. Let us see one by one. Look at that particular figure. In that figure, you will find that the material is subjected to pull type of loading. If it is get pulled, then it is break. So that is called as a tensile stress. The formula for tensile stress is force divided by area. Let us say about the second type of picture. In that there is a compression. Because of that there is a push type of loading. If there is a push type of loading on the material, then there is a compressive stress. It is also having formula force divided by cross section area. Area means cross section area. So only tensile and compressive both are having same formula. The direction is different. So symbol of tensile stress is sigma T, whereas symbol of compressive stress is sigma C. Force divided by cross section area. Only direction of loading is different. Now let us see third, shear stress. Shear stress, now tensile stress and compressive stress is along the axis. When we think about the loading like this type of loading, now axis of our bar is here, the force direction is like this, so it is a cutting of that particular part. So when this type of loading is there, you can observe violet color body is going to cut because of the direction of force. So that kind of stresses is called as a shear stress. It is generally denoted by tau, and this is also equal to force divided by area. So the third type of stress is direct shear stress. Direct shear stress means there is a direct loading perpendicular to the axis, and because of that there is a failure, and this is denoted by tau, which is force divided by cross section area. If that particular body is subjected to bending, so if this is the body and there is a force here and it is going to bend, because of the bending, there is a two type of stresses can be observed. If this particular cantilever or the simply supported beam, which is shown in the figure, subjected to force, then it is going to bend. When it is going to bend, on the upper surface there is a tensile stress, whereas the bottom surface there is a compressive action. So bending stress, will go in detail about this bending stress in our shaft chapter. So bending stress is denoted by sigma b, which is bending moment divided by section modulus. So we'll go in detail about the section modulus and bending moment in detail in the shaft chapter. Now next stress is crushing stress or bearing pressure. Crushing stress or bearing pressure, it is the one more kind of stress that you may not study in our strength of material. So crushing stress or bearing pressure is the type of stress which is caused due to crushing action. So whenever two parts are going to rub, or they are having compressive type of nature, then one part may get crushed by the other. So because of this, crushing stress or bearing pressure observed. So generally, if you just think about the our ball and ball bearing or our hinges, so in the inside that there is a crushing action. So there is a crushing action means the crushing action, because of that there is a wear and tear and there is a compressive type of loading. So that is denoted by PB. So that force divided by equivalent area under crushing is important. So that crushing stress is also we are going to see detail in our next chapter. The sixth type of stress is one more kind of shear stress which we call as a torsional shear stress. Now here we pull our body, we push our body, we bend our body, we crush our body. So last one is torsional. If I rotate our body, there is a torsional. Okay. So torsional stress is again a type of shear stress. This torsional stress also we are going to see in detail in the shaft chapter. So this is also denoted by tau. Now here shear stress which is in the third row is also a shear stress, but that is direct shear stress. This is torsional shear stress. It is also denoted by tau, which is equal to torque divided by polar section modulus. So in our bending stress also there is a section modulus. In our torsional stress also there is a section modulus. So what is the difference between that and how to find this torsional shear stress, that we'll understand in the next chapter. So this is all about types of stresses. So our complete elements of machine design is covered under all these types of different stresses. In next every topic we are going to see what kind of stresses are applied on that particular machine component and how to get dimensions of the safe dimensions of the machine component because of induced stresses. Okay. Now after the stresses, let us go further for our important one more concept which is called as a principal stresses. Principal stresses is the combination of different kinds of stresses. If I say our simple tensile, compressive, bending, shear, if I combine all this, because in practical condition our machine components subjected to combined stresses. It is not say that, for example, this is a particular machine component, it is having pull as well as it is having torque. So such type of condition observe in our day-to-day life. There may be chances that a particular machine component is having tensile type of stresses as well as torsional type of stresses. So if this particular machine component is subjected to direct tension as well as shear, then how we can find the total or normal stress or complete stress on the body, that we can say we can calculate by using this principal stresses. Principal stresses are the combined stresses which combines all the 6 stresses that we have already seen in our last slide. So we'll go in detail about the principal stresses wherever there is a combined type of loading. Okay, so this is about the principal stresses. Now next is, so here one more important machine behavior or component behavior that we are going to see here. So when any machine component is subjected to a type of stress, it observes changes in the stress and strain, and that particular observations are different for different kinds of material. Now here we are going to see a very simple object on the screen. The object is a cylindrical rod. That cylindrical rod is subjected to axial loading. Now there is a pull type of loading, means there is a tensile stress. So that particular body is subjected to pull. Then what is the behavior and what is the changes in the stress and strain, that we are going to see here. Now basically these stress and strain changes are differ for ductile type of material and for the brittle type of material. Here we'll see stress versus strain behavior, or which is also called as a stress strain diagram, for the ductile type of material. Ductile material means what? If you define a ductile material, it is the ability of material to drawn into wires. That means here the material, if I pull, then it can be drawn into thinner wire. So that is ductile material. So example, we can say that mild steel. Mild steel is a ductile one. Or we can say that our silver and copper, aluminium, all are ductile material, because you can find such type of material in our day-to-day life applications like electric wires. So if such ductile material is observed under the simple tension, just like a specimen which is shown here, then how the stress is going to change with the strain. Now let us start with our graph. You'll find that there is a stress on the y-axis and strain on the x-axis. Stress is defined as force divided by area, strain is defined as delta L by L. So that means if you say that F divided by A is constant because that is cross section area. That means stress is directly related with force, and strain is equal to delta L by L. L is constant, that means strain is delta L. So that means it is the behavior of the material which is depend upon force which is applied, which causes stress, and elongation which causes strain. So wherever there is a change in the force which is on the y-axis, there is a change in the strain. So that's why on the y-axis we have considered stress. Let us start from initial condition. Initially there is no force. There is no force means there is no strain. So our body is at zero condition. Now if I try to pull that, then what is the changes in the stress or strain? Look at the figure. I'm going to change the stress value. Now if you just see the figure, you will find that initially there is a graph between stress and strain. The graph is a straight line. That inclined line is having some slope. So that means already we have studied in our strength of material, there is a Hooke's law. What Hooke's law state? Stress is directly proportional to strain within the elastic limit. So elastic limit means here the stress is proportional. So wherever there is a stress change, there is a strain change. Wherever there is a force which is going to apply, there is a elongation. So that called a point as proportional limit. So here the slope of the line is constant, so stress is proportional to strain. Again, if I increase the force, now there is a short line which is observed on the screen, and the name is also there, elastic limit. So again, if I increase the load, then there is again straight line, and there is a limit to that. So that limit is called elastic limit. So Stress is proportional to strain within certain limit, which is called as elastic limit. So what is elastic limit? Elastic limit is the limit in which if I remove the force, then again material comes to its original position. So if I again try to pull that, and if I remove the load, again material will retain its original shape and size. So that is elastic limit. If I again increase the stress, if I again increase the force, what will happen? Let us check. So again it goes in upward direction, but there is a one more point come which is called as a yield point. Yielding means what? Now after elastic limit, the material behaves differently. Now after this elastic limit, material may not come to its original shape and size if the force is get removed. So that is called a yielding. Yielding means there is a large increase in the deformation. So if there is a large increase in the deformation, then there is a yielding point. Now here, after this yielding point, again if I increase the force, what will happen? So now after upper yield point, there is a lower yield point. So what is that lower yield point? If you just observe the figure, you will find that there is a negative direction of the that particular graph. Negative direction of the graph means here without application of force, there is an increase in the strain. Why? Because it is in this plastic zone. When the material is in the plastic zone, then obviously that particular material deform easily. So that is called lower yield point. So yielding means it is in the plastic zone, it will not retain its original shape and size. But after that, again if I increase the stress, then you will find that there is a curve like this. In that curve now there is a proportionality is not there. So if you observe that graph, the graph is having curve, so there is no any proportional relationship. And if you just observe the shape, it goes up to maximum and again it goes at that particular lower side. So theoretically and practically how this happen, that also we'll see. Now look at the our presentation. So you'll find that after lower yield point, there is a ultimate point. Ultimate point is the maximum point on which our stress is at the highermost position. So ultimate point is the maximum stress observed. Practically, there is a breaking point which is higher than the ultimate point, but as if you just look at the figure, you will find that there is a neck formation, there is a reduction in area. Because of the reduction area, we will observe the area is becomes lesser and lesser, and as F divided by A is the stress and A is going to reduce, that's why practically the breaking point is above the ultimate point. If you just take original our area, then you will observe that breaking point stress is lesser than the ultimate point. Here the important thing is that the ultimate point is the maximum stress point for any ductile material. So this is about the stress strain diagram and stress strain behavior of the ductile material. And this type of diagram also asks for 4 marks. With the description, it can be asked for 6 marks. So this is the stress strain behavior of ductile material. Now let us think about the stress strain behavior for brittle material. Now in the brittle material, you cannot observe any yielding. There is no any yielding. So same thing, same particular stress and strain behavior for the brittle material, you will find here like this. Okay, now look at the figure again. There is a proportional limit, there is elastic limit, but after the elastic limit, there is a sudden change. There is a sudden change in the stress with strain. Strain increases very faster, and at a particular point it breaks. So that is the ultimate point. So there is a sudden breaking. There is no any neck formation. There is no any reduction in area. Direct failure is there because it is a brittle material. The brittle material cannot have that much property to sustain tensile stress or tensile loading. It will break suddenly. Brittle material breaks suddenly with tensile loading. So that's why there is a direct breaking point for the brittle material. So in your exam, if the ductile material stress strain behavior is asked, you must draw the previous diagram. If it is asked for brittle material, this type of points should be there. So this is all about the stress strain behavior of brittle material. So this completes our load, stress and stress strain diagram for a particular different kinds of material. Now based on that, we are having some numericals now that we are going to see on the in the next few slides.